Tonight we are going to ask one of the simplest questions in science and discover that it has no answer. Not because we have not measured carefully enough, not because the instruments are not sensitive enough, but because the question itself contains a hidden assumption, an assumption so deep that most people never notice it is there, and the moment you see it, the universe looks different than it did before. The question is this: how fast are you moving right now? You are probably sitting still, or lying down. Your body is at rest relative to the floor, relative to the walls, relative to everything in the room. That is what still means to you. But astronomers will tell you that you are not still at all. They will give you a number in the millions of miles per hour. Cosmologists will add more layers. Physicists will say the situation is stranger than any of those numbers suggest. And here is where the story actually starts. Because those physicists are right. The real answer to how fast we are moving through deep space is not a bigger number than you expected. It is something that reframes the question entirely. By the end of tonight, you are going to understand why the word really in that question is the most important word. Why speed has no meaning without something to measure it against. And why there is one sense in which you are always, without exception, moving at exactly the same speed as everything else in the universe. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Sit quietly for a moment with the feeling of stillness. Not the idea of it, the actual physical sensation. Your body resting against whatever surface is beneath you. No sense of speed, no wind, no vibration that suggests you are traveling anywhere. You feel, in the most direct and immediate sense, completely at rest. This feeling is real. It is not an illusion in the way people sometimes casually say it is. You really are at rest relative to your surroundings. The floor beneath you is not moving relative to you. The walls are not moving. The air in the room is not rushing past you at millions of miles per hour. But here is the question that cuts to the heart of the matter. At rest relative to what? Your body is at rest relative to the floor. The floor is part of a building. The building is on the surface of a planet. That planet is orbiting a star. That star is orbiting the center of a galaxy. That galaxy is moving through a larger structure. And that structure is embedded in a universe whose space is itself expanding. Each of these is a real motion. Each of them is measurable. Each of them gives a different number for how fast you are traveling. And here is the uncomfortable truth that physics arrived at about a century ago. None of those numbers is more correct than any other. There is no measurement that gives the final true speed. There is no privileged place in the universe you can stand and measure your absolute velocity. Motion is not a property that things have on their own. It is a relationship between two things. And which relationship you choose to measure is not a physics question. It is a choice. This is not a philosophical trick. It is one of the most important experimental findings in the history of science. And understanding it properly requires us to first understand what was found, when it was found, and why it permanently changed the meaning of the word moving. In the late 1800s, physicists were convinced that space had a fundamental fabric. Not metaphorically, physically, they called it the luminiferous ether. The idea was that light, like sound, must travel through some medium. Sound travels through air. Remove the air and sound cannot travel. So what was light travelling through? The aether was the answer. an invisible, motionless substance that filled all of space. And if it was motionless, you could use it as an absolute reference frame. You could, in principle, measure your speed relative to the aether and get your true absolute velocity through space. In 1887, two physicists named Albert Michelson and Edward Morley built the most sensitive measurement device of their era to detect Earth's motion through the aether. They split a beam of light, sent the two halves in perpendicular directions, and measured whether the light travelling in the direction of Earth's motion through the aether arrived at a different time than the light travelling perpendicular to it. If the aether existed, the speeds would differ slightly. The answer came back. No difference. At all. Earth appeared to be completely stationary relative to the aether, which made no sense, because Earth was obviously moving around the Sun. They repeated the experiment. They refined the instruments. They waited 6 months so that Earth's direction through space had reversed. Still nothing. The aether did not exist. And without the aether, there was no motionless backdrop against which absolute velocity could be measured. Space itself turned out to have no preferred resting state, no built-in sense of still. This result sat uncomfortably in physics for nearly 20 years, until a young patent clerk in Switzerland named Albert Einstein understood what it meant. Einstein's insight in 1905 was not primarily about what Michelson and Morley found. It was about what their result implied. If there is no absolute rest, if no measurement can detect absolute motion, then there is no such thing as absolute motion. Speed is not a property an object has. It is a relationship between two objects. And every observer who measures the same event from a different state of motion will get a different answer for the speeds involved. Not because one of them is wrong, because they are both right from their own reference frames. This was not a statement about the limits of measurement. It was a statement about the nature of reality. Einstein then made a deceptively simple assumption to go with it. The speed of light in a vacuum is the same for every observer, regardless of how fast those observers are moving relative to each other. Not approximately the same. Not the same after correction factors. Exactly the same. Always, this assumption, combined with the absence of absolute rest, produces results that still feel strange after more than a century of confirmation. If you are moving at half the speed of light relative to me, and you shine a flashlight forward, you will measure the light from that flashlight moving at exactly the speed of light. And I will also measure the same beam of light moving at exactly the speed of light. Not the speed of light plus half the speed of light, just the speed of light. The only way both of those statements can be true simultaneously is if space and time are not fixed. If the length of a meter and the duration of a second actually change depending on how fast you are moving relative to something else. This is not a trick. It is what experiments confirm. And it means that the question of how fast you are really moving has no complete answer, because the answer depends entirely on what you are measuring your motion against. Choose different reference frames and you get different speeds, all of them equally valid, none of them the true one. So where does this leave us? It leaves us with something stranger and more interesting than any single speed could provide. Let us build the picture from the ground up, not as a list of layers, but as a sequence of choices, each one revealing something new about what motion means. If you measure your speed relative to the floor beneath you, the answer is 0. You are still. If you measure your speed relative to the center of the Earth, you are moving. The Earth rotates, and depending on where you are on its surface, you are being carried through space at somewhere between a few hundred and just over 1,000 miles per hour. Not because you are pushing against anything, simply because the planet is spinning and you are on it. If you measure your speed relative to the Sun, the number grows again. Earth is in orbit, moving at roughly 30 kilometers per second relative to our star. Every second, the ground beneath you has moved 30 kilometers through space relative to the Sun. Every hour, you have traveled more than 100,000 kilometers, not toward any destination. In a curve, because orbit is just a continuous fall where the sideways motion is fast enough to keep missing the thing you are falling toward. If you measure relative to the center of the Milky Way, the Sun is orbiting the galactic core, carrying the solar system with it. The orbit takes roughly 225 million years to complete. The speed is somewhere around 220 kilometers per second. The Milky Way is large enough that even at that speed, one complete lap around it takes longer than the dinosaurs have been extinct. If you measure relative to the cosmic microwave background, the faint afterglow of the early universe that fills all of space, the galaxy is moving at roughly 600 kilometers per second in a particular direction. This is currently the closest thing physicists have to a background reference frame for measuring cosmic motion, not because it is absolute, but because it is the most uniform and the most distant backdrop we can observe. Each number is real, each is accurately measured. And none of them is the correct answer to how fast you are really moving, because that question has no answer without a specified reference frame. But here is where the story takes its most unexpected turn. It helps to understand what astronomers actually measure when they say the galaxy is moving. Because the measurement is more subtle than it sounds, and understanding it properly shows why the layers of speed we are talking about are real, not estimates. When you look at a distant star or galaxy, you are seeing light that travelled through space before reaching your eye or your telescope. Light has a property that makes it a useful measuring tool for motion. When the source of light is moving toward you, the light waves are compressed, arriving at a slightly higher frequency than they would from a stationary source. The colour shifts toward the blue end of the spectrum. When the source is moving away from you, the waves are stretched, shifting toward the red end. This is called the Doppler effect, and astronomers use it constantly to measure how fast objects are moving toward or away from Earth. By measuring the spectrum of a nearby star, the precise colours and the positions of specific absorption lines that atomic physics predicts, astronomers can tell whether that star is approaching or receding and at what speed. By mapping thousands of stars and galaxies this way, they can build up a picture of how everything in our region of the universe is moving. What this picture shows is that our galaxy is not moving randomly. It is flowing. There is a coherent direction and speed to the motion, driven by the gravitational pull of mass concentrations in that direction. The cosmic microwave background provides the background against which this flow is measured, and the result is that the Milky Way and its neighbours are streaming at around 600 kilometers per second toward a particular region of the sky. 600 kilometers per second. It sounds fast, and it is. But in cosmic terms, even this enormous speed produces only tiny effects on astronomical timescales. The nearest large galaxy is still 2.5 million light-years away. At 600 kilometers per second, covering that distance would take more than 1 billion years. Our spatial motion is fast by any human measure and slow by any cosmic one. But the motion is real, it is measurable, and it is carrying us right now toward a particular region of the universe at a speed that no engineer has ever approached, and that you are experiencing without any sensation whatsoever. The absence of sensation is itself worth understanding carefully. Physics distinguishes between two kinds of motion: inertial motion, which is motion at constant velocity in a straight line, and accelerated motion, which is any change in speed or direction. The critical insight, one that Galileo had in the 1600s, and that Einstein formalized 3 centuries later, is that inertial motion is completely undetectable from the inside. If you are in a sealed room moving at constant velocity, there is no experiment you can perform inside that room that will tell you how fast you are moving or even whether you are moving at all. The physics inside the room is identical to the physics in an identical room that is stationary. This is not a limitation of measurement technology, it is a fundamental feature of how physics works. Newton's laws of motion look identical in every reference frame that is moving at constant velocity. Einstein's relativity extends this. Not just mechanical laws, but all physical laws, including the behavior of light, look identical in every such reference frame. This means the sensation of stillness you feel is not misleading you about your speed. It is telling you something real. You are in inertial motion. Nothing in the universe is pushing against you. You are simply moving, smoothly, continuously, with everything around you, in a way that produces no physical sensation. The Earth's rotation is slightly different. Rotation is not inertial motion because it involves constant change of direction, which is a form of acceleration. The centripetal acceleration of Earth's surface is real, and in principle you could measure it, but it is tiny, only about 1/3% of the normal gravitational acceleration at the equator, and far too small to feel directly. The orbit around the Sun is also technically accelerated motion, since orbital motion is continuous change of direction. But the acceleration is so small and changes so gradually over the course of a year that no instrument you carry on your body would ever register it. Everything above those scales, the Sun's motion around the galaxy's motion through space, the flow toward the cosmic attractor, all of it is inertial. No acceleration, no sensation. Just constant velocity through the cosmos. There is a question that naturally follows from all of this. If we cannot feel our motion, and if motion only has meaning relative to some chosen reference frame, why do astronomers bother measuring it at all? What is the point of knowing the galaxy is moving at 600 kilometers per second relative to the cosmic microwave background if that number does not correspond to anything physically privileged? The answer is that the number tells us things we would not otherwise know. Not about absolute motion, which does not exist, but about the structure of the universe. Every galaxy in the observable universe has a velocity. Some of that velocity is due to the expansion of space, which carries distant galaxies away from each other at rates that increase with distance. That part can be calculated from the Hubble law and subtracted out. What remains after that subtraction is called the peculiar velocity, the motion of a galaxy relative to what the expansion alone would predict. Peculiar velocities are informative precisely because they are not explained by expansion. They are driven by gravity. And gravity is driven by mass. By mapping the peculiar velocities of thousands of galaxies, including our own, astronomers can infer where the mass is, even mass that does not emit light and cannot be seen directly. This is how the large-scale structure of the universe was partly mapped before telescopes could resolve distant galaxy clusters directly. Astronomers watched how things moved and worked backward to figure out what must be pulling on them. The inferred mass matched, in general terms, what later observations confirmed when the technology improved. Our galaxy's peculiar velocity is a piece of evidence in that map. Where we are going and how fast tells us something about what is pulling on us, and what is pulling on us traces the distribution of matter in the universe at scales of hundreds of millions of light years. The speed of our galaxy through space is not just a curiosity, it is a data point in the largest map ever attempted. There is another layer of motion worth understanding, one that most accounts of cosmic speed never mention. Within the Milky Way, the stars are not all orbiting the galactic center in simple, neat circles. The galaxy is more complex than that. Stars follow orbits that are slightly elliptical, slightly tilted relative to the galactic plane, and perturbed by the gravitational influence of nearby stars, nebulae, and the dark matter halo that surrounds the galaxy's visible disk. The Sun itself has what astronomers call peculiar motion relative to the local standard of rest, which is the average motion of the stars near our position in the galaxy. The Sun is moving at about 20 kilometers per second relative to that local average, in a direction that carries it slightly toward the constellation Hercules. Over millions of years, the Sun bobs above and below the galactic plane as it orbits. The galactic disk is not infinitely thin. It has some thickness, and the gravitational pull from the disk's mass causes stars to oscillate through it, like a gentle wave motion that takes tens of millions of years to complete one cycle. During those cycles, the solar system passes through regions of slightly different star density. Some researchers have speculated about whether these density variations might influence the rate of comet impacts in the inner solar system by perturbing the distant reservoir of comets called the Oort cloud. The evidence is not conclusive, but the motion itself is real and measurable. The Sun's bobbing through the galactic plane is one more motion layered on top of the galactic orbit, on top of the solar system's motion, on top of the Earth's orbit, on top of the planet's rotation. Every one of these motions exists simultaneously. Every one of them is real in its reference frame. None of them is the final true speed. There is a version of the question that does have a single answer. An answer that is the same for every object in the universe. An answer that does not change regardless of what reference frame you choose. It comes from understanding not just speed through space, but speed through space-time. When Einstein published his special theory of relativity in 1905, and then extended it into the general theory in 1915, one of the most important ideas that emerged was this: space and time are not separate things. They are two aspects of a single four-dimensional structure called space-time. You move through space-time constantly, whether you want to or not. Even if you are sitting completely still in space, you are moving through time. Every second, a second passes. You are travelling through the time dimension at the rate of 1 second per second, which sounds trivial until you understand what it means in the full space-time picture. In that picture, every object is always moving through space-time at the same total speed. The speed of light, not through space at the speed of light, through space-time. The motion is divided between the space dimensions and the time dimension, and here is the critical part. The more of your space-time speed you use for moving through space, the less of it is available for moving through time. This is not an analogy. It is what the mathematics of special relativity actually describes. The concept has a precise name. Physicists call it the four-velocity, and it is one of the most quietly profound ideas in all of modern physics. Every object in the universe has a four-velocity. It is a vector, a quantity with both magnitude and direction, that describes motion through all four dimensions of space-time simultaneously. The magnitude of this four-velocity, the total speed of motion through space-time, is always exactly equal to the speed of light. For everything, everywhere, without exception. For an object at rest in space, all of that space-time velocity is directed through time. The object moves through time at the maximum possible rate. Clocks tick as fast as they possibly can. For an object moving through space, some of that space-time velocity is redirected from the time dimension into the space dimensions. The object moves through time more slowly. less time passes for it per unit of the outside world's time. This is not a hypothetical, it is the effect physicists call time dilation, and it has been measured with extraordinary precision. Atomic clocks on airplanes run slightly slow compared to identical clocks left on the ground. The moving clocks redirect a small fraction of their space-time velocity into spatial motion, and that means they tick more slowly through time. Satellites in orbit experience the same effect, and their onboard clocks require constant correction to stay synchronized with ground-based timekeeping. The faster an object moves through space, the more slowly it moves through time. The two are connected. They are trading against each other from a fixed total budget, and that budget is always exactly the speed of light. This means that the answer to how fast you are really moving through space-time is not a question at all. You are always moving at the speed of light. So is every other object in the universe. The differences between objects are not differences in their total space-time speed. They are differences in how that speed is divided between space and time. Let us sit with what this means for a moment. When you are at rest in a room, you are not moving through space, but you are moving through time. Every second of your life is a second of travel through the time dimension at the maximum possible rate, which is the speed of light through space-time. When a particle accelerator hurls a subatomic particle to within a fraction of a percent of the speed of light, that particle barely moves through time at all. Its total space-time velocity is still exactly c, but nearly all of it is pointed through space. Time for that particle has slowed to a crawl. The particle ages almost not at all during its transit. This is why physics says that nothing can travel faster than light through space, not because there is an invisible wall preventing it, but because the total space-time velocity is fixed at c, and you cannot redirect more than 100% of it. To move faster than light through space would require borrowing more than your total budget. And there is nothing to borrow. The speed of light is not a barrier, it is an accounting identity. It is what you get when you add up motion through space and motion through time, using the correct space-time geometry. The sum is always c, always the same for everyone. Always the four-velocity concept deserves more careful unpacking, because it is genuinely strange, and the strangeness is the kind that rewards sitting with rather than passing over quickly. In ordinary three-dimensional space, velocity is straightforward. You are moving in some direction at some speed, and the combination of direction and speed tells you everything about your motion. In four-dimensional space-time, the same logic applies, but with one important addition. You are always moving through time as well as space. And Einstein's geometry of space-time means that motion through time and motion through space are connected in a specific fixed way. Imagine your total space-time velocity as a quantity with a fixed magnitude. You cannot make it larger or smaller. It is always exactly c, the speed of light. But you can point it in different directions within the four dimensions. When you are at rest in space, your entire space-time velocity is directed through time. You are moving through time at the maximum possible rate. Your clock ticks as fast as it can. Now suppose you begin moving through space. To redirect some of your space-time velocity towards spatial motion, you must take some of it away from the time direction. Your spatial speed increases, but your motion through time decreases. Your clock runs more slowly, not because something is wrong with your clock, because you are genuinely moving through time at a slower rate. The formula that connects these is one of the most tested relationships in physics. For an object moving at speed v through space, the rate at which time passes for that object relative to a stationary observer is given by a factor involving v and c. When v is 0, the factor is 1, and time passes normally. As v approaches c, the factor approaches 0, and time stops almost completely. At everyday speeds, the difference is too small to measure without extremely precise instruments. At the speed of the galaxy through space, about 600 kilometers per second, the time dilation effect is about 1 part in a billion. Tiny, but real. Astronauts on the International Space Station, travelling at about 7.7 kilometers per second, experience time dilation that amounts to losing about 0.007 seconds per 6 months in orbit. That is enough to be measured. It is not enough to feel, but it confirms that the trade-off between spatial motion and time motion is real, not theoretical. The implications accumulate as speeds increase. A hypothetical spacecraft travelling at half the speed of light would experience time passing at about 87% of the rate experienced by someone stationary. Travelling at 99% of the speed of light, the onboard clock would run at about 14% of the outside rate. An astronaut who left Earth at 99% of C and travelled for what felt to them like 1 year would return to find that Earth had aged by about 7 years. This is not a paradox. It is what space-time geometry predicts. And the prediction is confirmed by every experiment sensitive enough to measure the effect. The universe is built so that fast motion through space always comes at the cost of slow motion through time. The two are not independent. They are different facets of the same underlying motion through space-time, and the total is always the same. Understanding why the speed of light is the universal constant in this picture requires one more step. The relationship between spatial motion and time motion is not arbitrary. It comes from the geometry of space-time itself. Einstein's special relativity describes space-time as having a specific mathematical structure, a geometry that treats time somewhat like a spatial dimension, but with a crucial sign difference. In this geometry, the space-time interval, the four-dimensional equivalent of the distance between two events, is calculated in a way that mixes space and time. The formula is similar to the Pythagorean theorem for ordinary distance, but with time contributing a term with the opposite sign. The result is a quantity that is the same for all observers regardless of their relative motion. The speed of light appears in this formula as a conversion factor between time and space. It is the factor that makes the dimensions compatible. The way a conversion factor between kilometers and miles makes length measurements in different units comparable. In this sense, the speed of light is not simply the speed at which light travels. It is a fundamental feature of the geometry of space-time. It is the factor that relates spatial distance to temporal duration in the unified four-dimensional structure of the universe. This is why nothing can exceed it. Not because there is a speed limit enforced by some external rule, but because c is built into the geometry itself. Exceeding c in spatial terms would require redirecting more than your total space-time velocity into spatial motion, leaving negative motion through time. And negative motion through time is not something the geometry of space-time allows. The universe is structured so that the maximum spatial speed is exactly the conversion factor between space and time. That conversion factor is the speed of light. And every object in the universe moves at exactly that total rate through space-time, always, without exception. The history of how physics arrived at this understanding is worth a brief tour, because the path was not obvious and the resistance was substantial. The idea that space and time are relative, that different observers measure different values for the length of a meter and the duration of a second violated deep human intuitions about reality. For millennia, time was understood as universal. the same everywhere, flowing at the same rate for everyone. A clock on Earth ran at the same rate as a clock on the Moon, on Mars, or on a distant star. Newton's physics assumed this explicitly. Time was absolute. Einstein did not begin by trying to overthrow Newton. He began by trying to resolve a specific puzzle about electromagnetism. The equations of electromagnetism, written by James Clerk Maxwell in the 1860s, predict that electromagnetic waves travel at a specific speed, the speed of light. But relative to what? The equations did not say, they simply gave a number. Newtonian physics would say that the speed of light should add or subtract depending on the motion of the observer. If you are moving toward a light source, the light should appear faster. If you are moving away, it should appear slower. But Maxwell's equations did not work that way. They predicted the same speed for all observers, and Michelson and Morley confirmed that the same speed was what was actually measured. Einstein took this seriously and followed the logic wherever it led. If c is the same for all observers, then the measurements of space and time must themselves be variable. What changes from one observer to another is not the speed of light. What changes is the ruler and the clock. He published the theory. It was tested. It passed every test. It passed tests that had not been imagined when the theory was written, and it passed them with the kind of precision that leaves no room for doubt. The universe, it turned out, was not built the way human intuition suggested. It was built around a fixed speed, and everything else, space, time, energy, mass, was arranged around that fixed speed in a geometry that we now call space-time. Now step back to the larger picture, to the layers of motion that astronomers measure. The Earth spinning, the planet in its orbit, the Sun circling the galaxy moving through space at hundreds of kilometers per second relative to the cosmic microwave background. Each of these is a real spatial motion. Each of them is measured relative to a different reference frame. And each of them, by the rules of space-time, means that the objects involved are redirecting a portion of their forward velocity from time into space. The Earth, moving at about 30 kilometers per second in its orbit, experiences time very slightly slower than it would if it were stationary relative to the Sun. The difference is tiny, but it is real. It is not a thought experiment. It is an effect that must be accounted for in satellite timing systems. The Sun, moving at 220 kilometers per second around the galaxy, experiences a slightly greater time dilation relative to the galactic center. Still small, but real. The galaxy itself, moving at around 600 kilometers per second relative to the cosmic microwave background, experiences an even greater time dilation relative to that background. None of these effects are large enough to be noticeable in daily life. But they are there. They accumulate, and they connect the casual observation of stars on a clear night to the deepest physics of space-time. When you ask how fast we are really moving, the physics answer is, completely at rest in space, you move through time at sea. Moving through space, you redirect some of that towards spatial motion. The faster through space, the slower through time. The total never changes. The trade-off is always exact. There is something worth understanding about how we figured out that the galaxy is moving the way it does. The cosmic microwave background is the relic light from when the universe was about 380,000 years old. A few 100,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that point, the universe was so hot and dense that light could not travel freely. After that point, light was suddenly free to move through space. And that light is still travelling today, cooled by the expansion of the universe into microwave radiation that fills all of space uniformly. When we map this microwave background with satellites, it appears almost perfectly uniform in every direction. The same temperature to extraordinary precision, regardless of where in the sky you look. Almost, not exactly. There is a very faint difference. One side of the sky is very slightly warmer, the opposite side is very slightly cooler. The difference is tiny, about 1 part in 1,000, but it is measurable, and what it measures is our motion. When you move toward a source of radiation, the waves are compressed slightly, which makes them appear warmer. When you move away from a source of radiation, the waves are stretched, which makes them appear cooler. This is the same effect that makes an ambulance siren sound higher in pitch as it approaches and lower as it retreats, called the Doppler effect. The faint temperature asymmetry in the cosmic microwave background tells us that we are moving relative to it at roughly 600 kilometers per second. Not the Sun alone, not just the Milky Way. The entire collection of galaxies in our local region of space, our supercluster, is flowing in that direction. This is the most comprehensive measurement of our motion that exists. It is, in a sense, our speed relative to the oldest light in the universe, our speed relative to the moment when the cosmos first became transparent. And it is still not an absolute speed. Even the cosmic microwave background is a reference frame, not an absolute backdrop. But it is the largest and most uniform backdrop available to us, which is why cosmologists treat it as the closest thing to a universal reference frame for measuring large-scale cosmic motion. The direction of our motion is as interesting as the speed. At the largest measurable scales, our galaxy and its neighbours are flowing in a direction astronomers have identified but cannot fully explain. The flow converges toward what is called a region of convergence, a direction in the sky toward which a broad swath of the nearby universe seems to be streaming. This convergence is driven by gravity. The universe is not uniform. Some regions have slightly more mass than others, which means their gravitational pull is slightly stronger, which means matter flows toward them over billions of years. The flow we measure in the galaxy's motion is the current snapshot of that process. There is a vast concentration of mass in a particular direction, behind the dense plane of the Milky Way itself, which makes it difficult to observe directly. The mass there is enormous, and it has been pulling on our galaxy, on our neighbours, on entire clusters of galaxies, for billions of years. Our motion through space is not just motion, it is a record. Every galaxy's velocity is a data point in the map of how matter is distributed in the universe. By measuring how things are moving, astronomers can infer where the mass is, even the mass they cannot see directly. The direction we are travelling tells us something about the structure of the cosmos at scales we cannot photograph. We are not just passengers in this flow. Our motion is a measurement instrument. The direction and speed of our travel through space is a piece of information about the universe's large-scale architecture. The cosmic microwave background deserves more attention than it usually gets in conversations about how we know what we know about our cosmic motion. When the universe was about 380,000 years old, it crossed a threshold. Before that moment, the temperature was high enough that hydrogen atoms could not remain neutral. Any electron that attached to a proton was quickly knocked free again by the energetic radiation filling the universe. The matter and radiation were in constant, intimate contact. The universe was opaque. Light could not travel any significant distance without being absorbed and re-emitted. Then the temperature dropped low enough for neutral hydrogen to form and persist. And in a relatively short time, by cosmological standards, the universe became transparent. Photons that had been bouncing around in the hot, dense plasma were suddenly free to travel. and they have been travelling ever since. Those photons are the cosmic microwave background. They have been travelling for about 13.8 billion years. The expansion of the universe has stretched them from visible light, or near it, down into the microwave range, which is why we detect them with radio-sensitive instruments rather than optical telescopes. But they carry information from that moment of release. The pattern of slight temperature variations in the background records the density variations in the early universe. The seed fluctuations from which all the structure we see today, galaxies, clusters, filaments, voids, eventually grew. And the overall direction and speed of our motion relative to this background is encoded in the large-scale temperature gradient across the whole sky. When the COBE satellite mapped the background in the early 1990s, and when WMAP and then the Planck satellite improved the map with increasing precision, the dipole anisotropy, the faint, warm, cool gradient that reveals our motion, was among the first and most clearly measured features. It was not hidden in the data. It was one of the largest signals in the map. From that signal, our speed relative to the cosmic microwave background was measured at about 620 kilometers per second toward a specific point on the sky. That direction falls roughly in the direction of the constellation Centaurus, toward the concentration of mass that has been pulling on this region of the universe for billions of years. This measurement is as close as physics can currently get to answering the question of our true cosmic speed. Not because the background is an absolute reference frame in the old discredited ether sense, but because it is the most uniform, most distant, and most precisely measured backdrop available to us. Measuring our speed relative to it is measuring our speed relative to the early universe itself, which is as fundamental a reference as currently exists. And even this is not absolute. Another civilization in a galaxy moving at a different peculiar velocity would measure a different speed relative to the same background. Both measurements would be equally correct. The question of reference frames in physics has a history that is worth knowing because it connects the everyday experience of stillness to the deepest architecture of the cosmos. Galileo Galilei was the first person to articulate clearly what physicists now call the principle of relativity. In his writings about motion in the early 1600s, he offered a thought experiment about a ship at sea. Imagine you are below decks in a cabin, he said, with no way to look outside. You have fish in a bowl, butterflies in a jar, and you can perform any experiment you like. Now suppose the ship is moving smoothly through calm water at a steady speed. Is there any experiment you can do to detect the ship's motion? Galileo's answer was no. The fish swim the same way. The butterflies fly the same way. Objects fall the same way. The physics is identical whether the ship is moving or stationary, and this means there is no physical fact of the matter about whether the ship is moving or stationary in any absolute sense. Motion can only be measured relative to something else. Galileo was writing about mechanical motion. He had no way to extend this to light. That came 3 centuries later. Newton refined Galileo's work and built classical mechanics on the foundation that all inertial reference frames are equivalent for mechanical experiments. But Newton retained the concept of absolute space and absolute time. He believed that even if motion was relative in practice, there was in principle an absolute position and an absolute rate of time. God's reference frame, as it were, the true resting state of the universe. Einstein dismantled this last remnant, not by argument or philosophical preference, but because the experimental evidence demanded it. If the speed of light is the same in all inertial reference frames, and Michelson and Morley had shown that it was, then there is no absolute rest. Not even God's reference frame. The universe simply does not have one. The transition from Newton's physics to Einstein's is, in one sense, a story about giving up the concept of absolute rest. And once that concept is given up, the question of how fast we are really moving loses its grip. Really fast relative to what? There is no absolute answer. There can be no absolute answer. Let us think about what it would mean to be genuinely motionless. In a Newtonian universe, being motionless meant being stationary relative to absolute space. It was a well-defined state, even if no practical measurement could identify it. Something was either truly at rest, or it was not, even if you could not tell from inside your reference frame. In Einstein's universe, being motionless is not a well-defined state for spatial motion. Every object can only be at rest relative to some other specific thing. There is no universal resting state. If you are at rest relative to your chair, you are moving relative to the sun. If you choose to be at rest relative to the sun, you are moving relative to the galactic center. If you choose to be at rest relative to the cosmic microwave background, you are moving relative to, say, a galaxy that is streaming towards you on its own peculiar velocity. No matter what spatial speed you choose, you are moving relative to something, and no matter what spatial speed you choose, some other observer will correctly describe you as moving at a different speed from their valid reference frame. The only motion that is universal, that every observer in every reference frame agrees on, is the space-time motion, the four-velocity, and that is always c. This is one of the most counterintuitive results of 20th century physics. The thing that appears most variable, speed through space, depends entirely on the reference frame. The thing that appears most universal and fixed, the speed of light, is fixed precisely because it equals the total space-time velocity that every object always has. C is invariant because it is built into the geometry. It cannot be different in different reference frames because it is not a motion through space. It is the total motion through space-time itself. General relativity adds another layer to this picture, and it is the layer most directly relevant to the cosmic motions we have been discussing. Einstein's general theory of relativity, published in 1915, extended the special theory to include gravity. The key insight is that gravity is not a force in the traditional sense. It is a curvature in the geometry of spacetime itself. Mass and energy curve spacetime, and objects moving through curved spacetime follow paths called geodesics, which are the four-dimensional equivalent of straight lines. When the Earth orbits the Sun, it is not being pulled by an invisible rope called gravity. It is following a geodesic through the curved spacetime produced by the Sun's mass. The path curves because spacetime itself is curved in that region. To an observer following a geodesic in curved spacetime, the motion feels like free fall. There is no sensation of force. This is why astronauts in orbit feel weightless. They are not above gravity. They are in free fall through curved spacetime, following a geodesic. The space station and everything in it is falling together, so there is no relative motion between astronauts and their environment, and no sensation of weight. The large-scale motions of galaxies are also geodesic motion. The Milky Way is following its geodesic through the curved spacetime produced by the mass distribution of the universe, including the enormous concentrations of mass toward which it is streaming. The motion feels like nothing from inside, but it is real, measurable, and consequential. The curvature of space-time, driven by the distribution of mass and energy in the universe, is what determines how things move at cosmic scales. Dark matter, the invisible substance that makes up the majority of the mass in galaxies and galaxy clusters, contributes enormously to this curvature. Dark energy, the even more mysterious component that drives the accelerating expansion, affects the large-scale curvature of spacetime in ways that cause distant regions to accelerate away from each other, Every cosmic motion we have discussed, the orbit around the galaxy, the flow toward the cosmic attractor, the recession of distant clusters, is a consequence of space-time curvature driven by the distribution of matter and energy across the observable universe. The question of where we are going is different from the question of how fast we are moving, but it follows naturally from it. Over the next several billion years, the motions we can currently measure will carry the Milky Way and the Andromeda Galaxy toward each other. These two galaxies are not moving apart the way most distant galaxies are, carried away from each other by the expansion of space. They are close enough, and their mutual gravitational attraction is strong enough that they are on a converging path. The collision will not look like the collisions of everyday experience. Galaxies are mostly empty space. The vast distances between stars mean that when two galaxies interpenetrate, individual stars almost never actually collide. What happens instead is a dance of gravity on an enormous scale. The two spiral structures will distort. Streams of stars will be flung out into long tidal tails stretching across hundreds of thousands of light years. The two galactic centers will pass through each other, drift apart, fall back, pass through again, and eventually, over hundreds of millions of years, merge into a single larger galaxy. Our Sun will almost certainly survive this process. It will be gravitationally perturbed, likely ejected into a different orbit in the merged galaxy. But the planet around it, and whatever exists on that planet at that point in time, would not experience the merger as a catastrophe. The star density would briefly increase. The night sky would look different. But the fundamental conditions for planetary life would probably not change dramatically. This is where our current motion is taking us. Not toward emptiness, toward merger. The galaxies around us are not flying away, they are falling in. The expansion of space operates differently from the motion of galaxies through space. And the distinction matters for understanding what our motion really means. When astronomers say the universe is expanding, they do not mean that galaxies are moving through space away from each other the way cars drive away from a city. They mean that space itself is stretching. The fabric of the universe is growing larger, and galaxies are being carried apart on that stretching fabric the way dots painted on a balloon move apart as the balloon inflates. This distinction is not just semantic. It has physical consequences. On small scales, gravity wins. The atoms in your body are not flying apart because space is expanding between them. Gravity holds them together. The Earth is not being pulled away from the Sun by expansion. Gravity binds the solar system. The Milky Way is not being disassembled. Gravity holds the galaxy together. But on very large scales, where gravity between distant galaxy clusters is too weak to overcome the expansion wins. Galaxy clusters beyond our local neighborhood are receding, and the rate of recession increases with distance. Galaxies far enough away are receding so fast that light from them will never reach us. They are beyond a horizon, not a physical wall, but a causal one. A point beyond which information cannot travel fast enough to cross the expanding gulf between us. This means that our cosmic neighborhood will eventually become an island. Not now, not soon in any human sense. But over billions of years, the observable universe from Earth's perspective will shrink. The galaxies that currently populate the night sky beyond our local group will recede beyond the horizon. Their light will stop arriving. The sky will darken. The motion that matters most in the long term is not the motion of our galaxy through space. It is the expansion of space itself. And that expansion is driven by something physicists call dark energy, a property of space that causes it to stretch at an accelerating rate. What exactly dark energy is remains unknown. It is the dominant form of energy in the universe, making up roughly 68% of the total energy content, and its effect on motion is to gradually pull the largest structures apart, no matter how fast those structures are otherwise moving through space. There is one more concept that connects the physics of space-time to the lived experience of motion, and it concerns what happens to time itself when you change how fast you move. We have already established that moving faster through space means moving more slowly through time. The two trade against each other from a fixed budget. But this means something practical and somewhat strange. Your choice of how to move through space is also a choice of how to move through time. If you could choose to orbit the Earth at orbital speed, about 7 kilometers per second, your clock would run slightly slower than a clock left on the ground. Not by much. About 0.007 seconds per 6 months. But the effect is real and must be corrected in GPE satellite systems, where timing precision is critical. If you could travel at 10% of the speed of light, your clock would run at about 99.5% of the rate of a stationary clock. For every 200 seconds that passed for you, about 201 seconds would pass for someone at rest. Still a small difference, but growing. At half the speed of light, your clock runs at about 87%. For every 10 years you experience, about 11.5 years pass outside. At 99% of light speed, your clock runs at about 14%. For every year you experience, about 7 years pass outside. At 99.9%, about 4.5% rate. For every year of your subjective experience, more than 22 years pass outside. The consequence of this is that hypothetical travelers moving at high fractions of the speed of light could cross enormous distances while experiencing only a small fraction of that time. A traveller at 99.9% of light speed heading for a star 100 light years away would arrive in about 100 years of outside time, but would have experienced only about 4.5 years. For them, the transit was not nearly as long as the distance in light years suggests. This is sometimes called the relativistic travel advantage. It does not violate any law. The outside universe ages 100 years. The traveller ages 5 years. Both are equally real. They simply experience different amounts of time covering the same distance. What makes this relevant to the question of our cosmic motion is that the everyday speeds at which the galaxy is moving produce real but tiny versions of this effect. We are all experiencing time at a very slightly different rate than we would if the galaxy were not moving relative to the cosmic background. The difference is negligibly small at galactic speeds. But it is there. The practical consequences of our cosmic motion on everyday life are, to be accurate, close to non-existent. The planet's rotation at the equator produces measurable effects on weather patterns. The atmosphere, the oceans, and the slow drift of continents are all influenced by the fact that Earth is spinning. These effects are real and important for understanding climate, navigation, and geology. The orbit around the Sun defines the seasons, drives the evolution of life through its influence on climate cycles, and provides the calendar by which every human civilization has organized time. Beyond those effects, the spatial motion of the solar system through the galaxy and the galaxy through the larger cosmos have no direct practical consequences for life on Earth. The gravitational tidal effects of other stars are too distant to produce measurable changes on human timescales. The occasional passage through a slightly denser region of the interstellar medium is thought to be negligible in its effects on Earth's climate. Our enormous cosmic velocity is, for all practical purposes, irrelevant to existence on this planet, and yet knowing about it changes something, not because it has practical consequences. but because it reveals the actual scale of the context in which we exist. You live on a planet, in a solar system, in a galaxy, in a universe. Each of those scales is vastly larger than the one before, and at each scale, the motion is real, the physics is consistent, and the same laws apply. The rules that govern a ball rolling down a hill also govern the motion of the Milky Way through the cosmic web. The trade-off between spatial motion and temporal motion that you can see in GPS corrections applies equally to a galaxy streaming toward an attractor at 600 kilometers per second. The universe is not divided into the physics of human scales and the physics of cosmic scales. It is one system, operating under one set of rules across all scales simultaneously. The question of whether we are moving toward anything in particular is one that cosmology has only recently been able to address with any precision. For most of human history, the answer was simply, we do not know. The stars appeared fixed, the planets moved against the background of stars, but those motions were local within the solar system. What lay beyond the visible stars was unknown. The discovery of the structure of the galaxy in the early 20th century showed that the Sun orbits the galactic center. The discovery of other galaxies showed that the Milky Way itself is in motion relative to its neighbors. The mapping of the cosmic microwave background revealed the direction and speed of that motion with precision. The destination, loosely speaking, is the concentration of mass in a particular region of the sky, driven by the accumulated gravity of hundreds of thousands of galaxies over billions of years. This concentration has been pulling on our galaxy for as long as our galaxy has existed. In that time, the galaxy has moved an enormous distance toward it, and it will continue to move in that direction. But the destination is not a fixed point. It is itself moving. The whole ensemble of galaxies, our local group and its neighbors, is flowing together toward the gravitational attractor. The attractor itself is part of a larger structure that has its own motion within the even larger cosmic web. The cosmic web is the name astronomers give to the large-scale structure of the universe. The vast filaments of galaxies connected at dense nodes, surrounding enormous voids of nearly empty space. Every galaxy in the universe is embedded in this web. Every galaxy's motion is a response to the gravitational landscape of that web. And the web itself is evolving, its densest regions growing denser as more matter flows in. Its voids growing emptier as matter drains out toward the filaments. We are flowing along a filament of the cosmic web. Our destination is not empty space. It is the slowly growing knot where our filament meets others, in a direction astronomers can now point to precisely, in a sky that at night appears completely still. Return for a moment to the four-velocity idea, to the fact that everything in the universe moves through space-time at the speed of light, divided between space and time. There is something in this idea that goes beyond physics. It connects to what it means to be alive and aware inside a universe that is always moving. You are not stationary. You never were. Every moment of your existence, you have been moving through time at the maximum possible rate, because you have been nearly at rest in space. Every second of your life has been a second of travel at the speed of light through the time dimension. Every year you have lived, you have moved 1 light year through time. You have covered light years of space-time distance just by existing. The stars in the sky that seem so impossibly far away are, in their own way, doing the same thing. Moving through space-time at sea, trading spatial speed for time, or time for spatial speed, in the constant rebalancing that space-time requires. And the cosmos around you, with its spinning planets and orbiting stars and flowing galaxies and expanding voids, is the aggregate of all those individual motions. Every object following its own path through space-time. every path through space-time summing to the same total velocity. Everything moving, always at the speed of light. This is what the word really in the title was pointing toward. Not a bigger number, not a more impressive speed, but a different kind of answer. One that dissolves the question of how fast we are really moving and replaces it with something more complete. We are moving through space-time at sea. We always have been. We always will be. The concept of simultaneity is one of the stranger consequences of the relativity of motion, and it connects directly to the idea of cosmic speed in a way that most accounts of cosmic motion overlook. In Newtonian physics, simultaneity was absolute. If two events happened at the same moment in time, they happened at the same moment for everyone, everywhere in the universe. A universal now existed. You could, in principle, point to any two events in the cosmos and say which came first, which came second, or whether they were simultaneous. Einstein's relativity destroyed this. Two events that are simultaneous in one reference frame are not simultaneous in a different reference frame that is moving relative to the first. This is not a measurement limitation. It is a fact about the structure of space-time. Here is a simple version of why. Imagine a train moving at high speed through a station. Two bolts of lightning strike both ends of the train at the same instant, according to an observer standing at the center of the station. From the station observer's perspective, the two strikes are simultaneous. But from the perspective of an observer at the center of the moving train, the situation is different. The light from the front strike reaches them slightly before the light from the rear strike, because they are moving toward the front. Accounting for the motion, they calculate that the front strike happened before the rear strike. Both observers are correct. Both calculations are internally consistent with the physics of their reference frames. There is no privileged frame that defines which calculation represents the true order of events. Now extend this to cosmic motion. Two galaxies at different positions in the universe are moving at different velocities. They each have a different definition of what simultaneous means. Events that are simultaneous from one galaxy's reference frame are not simultaneous from another's. This means that even the phrase "the universe right now" is not a well-defined concept. There is no single moment that is the present for the entire universe. Different observers at different positions and velocities have different definitions of the present. The universe does not have a single now that everything participates in simultaneously. This is uncomfortable. It feels wrong. Our intuitions about time are deeply built around the idea of a shared present moment. But the physics is clear, and it has been confirmed by every test capable of measuring it. What this means for the question of our cosmic motion is subtle but profound. When we say the galaxy is moving at 600 kilometers per second relative to the cosmic microwave background, we are describing something real and measurable. But when we try to extend that to a picture of the whole universe at this moment, all of it frozen in a single instant, we run into the problem that no such single instant exists universally. The universe is not a thing that exists at a moment. It is a four-dimensional structure, and our motion through it is motion through all four dimensions, not just three. Most conversations about cosmic speed focus on the scales that feel most dramatic. The galaxy moving at hundreds of kilometers per second. The Earth at tens of kilometers per second. These are the numbers that make the stillness of the room feel surprising. But there is a quieter and in some ways more profound version of the same story that concerns light itself. Light, in Einstein's universe, does not experience time. This is a strange statement, but it follows directly from the four-velocity picture. Photons, the particles that make up light, travel at c through space. That means they use their entire space-time velocity budget on spatial motion. Nothing remains for time motion. A photon does not experience the passage of time. From a photon's perspective, if we can loosely imagine such a thing, it leaves its source and arrives at its destination instantaneously. There is no duration in between. The 8 minutes of travel time that light takes to get from the Sun to Earth is 8 minutes from the Earth's perspective. From the photon's perspective, it is 0. The ancient starlight that crosses the night sky has not aged during its transit. A photon that left a star 1,000 light years away 1,000 years ago has not experienced 1,000 years. It has experienced nothing at all in terms of time. This is one of the most alien facts in physics. Everything with mass experiences time, even if it experiences it at a slowed rate when moving fast. Photons, which have no mass and move at exactly c, experience no time whatsoever. They are, in this specific sense, outside of time, born at emission, arriving at absorption with nothing in between. The universe, from a photon's perspective, has 0 size in the spatial direction of travel, and 0 duration in time. The photon exists only at the moment of creation and the moment of absorption. Everything between is collapsed to a point. This is the extreme limit of the trade-off between spatial motion and time motion. At exactly c, all time motion goes to 0. The clock stops completely. We, moving at a tiny fraction of c through space, experience time at something very close to the maximum rate. But the connection between our experience of time and the maximum possible rate is a direct consequence of how slowly we move through space. Our sense of time flowing, of moments passing, of years accumulating, is the direct experience of having most of our force velocity pointed through the time dimension rather than the space dimensions. We experience time richly precisely because we move through space so slowly. There is a philosophical resonance to this that deserves acknowledgement. The faster you move through space, the slower you move through time. The slower you move through space, the faster you move through time. The exchange is exact and universal. This means that everything you experience as temporal, the passage of moments, the accumulation of memories, the aging of your body, the sequence of events from past to future, is a consequence of being at rest in space. A consequence of not redirecting your space-time velocity into spatial motion. And the universe around you, moving at various speeds through space, is experiencing time at slightly different rates. Nothing dramatic in most cases. The differences at everyday cosmic speeds are too small to notice. But the differences are real. The Sun, moving at 220 kilometers per second around the galactic center, has been ticking slightly slower than a hypothetical stationary clock since its formation 4.6 billion years ago. The accumulated time difference is a matter of years out of billions. Small, but real. The galaxy, moving at around 600 kilometers per second relative to the cosmic microwave background, has been accruing a slightly different amount of time than a hypothetical galaxy at rest relative to that background. The difference accumulates over the 13 billion years since the early universe. These effects are not large enough to change the gross history of the universe. Stars formed when they formed. Planets coalesced when they coalesced. Life emerged on Earth on its own timeline. None of this would be different if the galaxy happened to be moving at a slightly different speed. But the fact that every object in the cosmos is moving through space-time at c, trading spatial speed for time speed in a precise and universal exchange, gives the universe a kind of deep symmetry that is easy to miss when you are focused only on the speeds in space. The stillness you feel right now is not an absence of motion. It is the full investment of your space-time velocity into time. It is you moving through time as fast as physics allows. It is you, right now, at the maximum rate of temporal experience. Nothing is more fundamental to what you are doing in this moment than that. The way we came to know this is worth sitting with briefly, because it is a story about the relationship between observation, experiment, and willingness to abandon assumptions that felt permanent. The aether was not abandoned easily. Physicists loved it. It made sense. Every wave they had ever studied needed a medium. Sound needed air. Water waves needed water. Light waves, they were certain, needed something. Michelson and Morley did not set out to disprove the aether. They set out to measure Earth's motion through it. The absence of any signal was a result neither of them initially wanted. Michelson spent years repeating and refining the experiment, hoping to find the effect he was sure must be there. It was not there. And Einstein's response to that absence was not to question the experiment. It was to take the results seriously and ask what the universe must be like if this result is correct. What must be true about space, time, and light if no observer can ever detect absolute motion? The answer was special relativity, and it turned out to match every subsequent experiment with extraordinary precision. GP's satellites would not function without relativistic corrections to their onboard clocks. Particle accelerators would not work without the equations of special relativity telling engineers how particles behave at high speeds. Nuclear reactions in the Sun, which keep us alive, follow exactly the energy-mass relationship that Einstein's theory predicts. The question of absolute motion turned out not to be a question with a missing answer. It turned out to be a question built on a false premise. The universe does not have an absolute resting state. It has reference frames, all of them equally valid, none of them special. And from that absence of specialness, something more meaningful emerged. The concept of proper time, which is what physicists call the time measured by an observer's own clock on their own world line, is the most personal measurement in physics. Every object in the universe has a world line. It is the path that object traces through four-dimensional space-time, from its creation to its destruction. For a star, the world line begins in a collapsing gas cloud and ends in a white dwarf, neutron star, or black hole. For a person, it begins at birth and ends at death. The proper time of a world line is the total time measured by a clock that travels along that world line. It is the subjective time experienced by the object itself. Two world lines that start at the same event and end at the same event can have different proper times, depending on the path taken through space-time. An observer who travels a longer spatial path through space-time will have a shorter proper time. An observer who stays nearly at rest will have a longer proper time for the same pair of events. This is the twin paradox, though it is not really a paradox once you understand space-time geometry. One twin stays on Earth, the other travels at high speed to a distant star and returns. When they reunite, the travelling twin has aged less than the stay-at-home twin. The difference in their proper times is real and measurable. They are genuinely different ages when they meet again. What makes this not a paradox is that the two world lines have genuinely different shapes in space-time. The Earth-bound twin follows a nearly straight path through space-time. The travelling twin follows a bent path, one that turns around at the distant star and comes back. The bent path through space-time is shorter in terms of proper time than the straight one. The phrase shortest path in space-time might seem backwards. Normally, straight lines are shorter than bent ones. But in space-time geometry, the sign convention for time is opposite to that for space, which means the calculation works in the counterintuitive direction. The straight, motionless path through space-time is the one with the most proper time. Being at rest in space means taking the longest possible path through time. Moving through space means taking a shorter path through time, even if the spatial distance covered is larger. This is the deepest meaning of the four-velocity picture. Every object is always moving through space-time at c. Objects at rest in space are maximizing their proper time. Objects in fast spatial motion are minimizing it. Your life, experienced from the inside, is your proper time along your world line. The accumulated moments of your existence are the total space-time path length of that world line, measured in the direction of time, and the rate at which you accumulate those moments, the rate at which your clock ticks, is determined by how much of your four-velocity is directed toward time versus space. At the speeds we move through space, the difference from maximum rate is negligible. But the connection is real. You experience time as you do because of the geometry of the space-time you inhabit and the velocity you carry through it. The question of how we know the age of the universe is deeply connected to the question of how we measure our motion through it. The universe has an age, roughly 13.8 billion years, because it had a beginning. The beginning was the Big Bang, not an explosion in space, but an expansion of space itself from an extraordinarily hot, dense state. In the earliest moments, the universe was so small and so hot that the physics we know breaks down. There was no space and time as we understand them. There was a singularity, or something close to it. As the universe expanded and cooled, space grew. The matter and energy within it diluted and organized. Atoms formed, light was released, stars condensed from clouds of hydrogen, galaxies assembled from billions of stars. And through all of this, the universe kept expanding. The expansion means that the universe has a finite age. You can trace the expansion backward, like running a film in reverse, to a moment when the universe was infinitely small and infinitely dense. That moment, or rather the earliest moments just after it, was about 13.8 billion years ago. But the age of the universe is measured from a particular reference frame, the cosmic microwave background, the rest frame of the average matter in the universe. The universe's age of 13.8 billion years is the time elapsed as measured in that frame. If you were moving at a high fraction of the speed of light relative to that frame, you would measure a different age for the universe. Not because the universe would actually be a different age, but because your clocks run differently. Your measurement of 13.8 billion years would differ from the measurement of an observer at rest in the CMB frame. In practice, nothing moves fast enough relative to the CMB frame for this to produce a large discrepancy. Our galaxy moves at about 600 kilometers per second, which is fast, but still a very small fraction of c. The resulting time dilation means that our clocks run at about 99.9998% of the rate they would at rest in the CMB frame. The discrepancy amounts to a few 100,000 years over the lifetime of the universe. Trivial on cosmic scales, but real. This is another reminder that the scales on which cosmic motion operates, while vast by human standards, are still small compared to the scales on which relativistic effects become dramatic. We exist in a universe where the relevant speeds are extraordinary by any everyday measure, and still modest compared to the ultimate speed limit. The connection between speed and gravity adds one more dimension to this picture. General relativity showed that gravity and acceleration are locally equivalent. A person in an accelerating rocket feels a force pushing them toward the floor. A person standing on the surface of the Earth feels the same kind of force from gravity. From inside a sealed room, no experiment can distinguish between the two situations. This equivalence principle, as Einstein called it, leads to the conclusion that gravity affects time. A clock in a strong gravitational field, such as near a massive star, runs more slowly than a clock far from any massive object. The effect is called gravitational time dilation, and it is distinct from the time dilation caused by relative motion. Near the surface of Earth, the gravitational time dilation is small but measurable. Clocks at sea level run slightly slower than clocks at the tops of mountains, because they are in a slightly stronger gravitational field. The difference amounts to about a few microseconds per day. GPS satellites must correct for both effects: the slowing of their clocks from moving through space, and the speeding up of their clocks from being farther from Earth's gravity than ground-based clocks. This means that our position in the gravitational landscape of the cosmos also affects how we experience time. We are embedded in Earth's gravitational field, which is embedded in the Sun's gravitational field, which is embedded in the galaxy's gravitational field, which is embedded in the larger structure of the local cosmic web. Each of these contributes a small gravitational time dilation. The total effect is tiny compared to our daily experience of time. But it is real, and it means that the question of how fast we are moving is inseparable from the question of where we are in the gravitational structure of the universe. Motion through space, position in a gravitational field, and passage through time are all connected. They are aspects of the same four-dimensional geometry. And that geometry is the universe. There is one more thing to say about time dilation that connects the physics directly to the experience of being a conscious observer in the universe. Every act of perception takes time. Light enters your eye and signals travel to your brain. The brain processes those signals and constructs an experience. The entire process takes a small fraction of a second, but it is a sequence of events with a definite duration. This means that your experience of any moment is already slightly in the past by the time you are aware of it. You are not experiencing the universe as it is. You are experiencing the universe as it was, a tiny fraction of a second ago, after the light from the scene around you has travelled to your eye and your brain has processed it. For nearby objects, this delay is negligible. The far wall of a room is close enough that the light travel time is a small fraction of a microsecond. For the Moon, the delay is about 1.3 seconds. For the Sun, about 8 minutes. For the nearest star, 4 years. When you look at the night sky, you are not seeing the present. You are seeing a layered record of the past, with each star and galaxy appearing as it was when the light you are seeing left it. The depth of the sky in time is far greater than its depth in space, and the motion of everything in that sky, including the motion of the galaxy you are sitting in, is adding a tiny but real-time dilation to every measurement. Every object moving through space is moving through time at a different rate than a hypothetical stationary observer would. The universe is not a collection of objects existing simultaneously in a shared present. It is a four-dimensional structure in which different objects are at different points in time, travelling through time at different rates and experiencing different proper times along their different world lines. The concept of the universe right now, a single frozen instant containing everything that exists, is not a physically meaningful concept in Einstein's physics. There is no global now. There is only the local now of each observer, determined by the path that observer has taken through space-time and the velocity they are carrying. The stillness you feel in this moment is your position on your world line. The sky above you is a window into countless other world lines, most of them very nearly parallel to yours in space-time, a few of them very different. And the connection between all of them is the one speed that never changes, the only motion that is universal, the total velocity through space-time, which is always, for everything, everywhere, at every moment in the history of the cosmos, exactly c. Not approximately c. Not close to c. Exactly c. What is the most honest answer to the question this script began with? You are moving at the speed of light through space-time. That is always true. It is true for you, for the planet beneath you, for the galaxy around you, for the furthest objects we can detect. The speed of motion through space-time is constant and universal. Within that space-time motion, your spatial speed depends entirely on what you measure it against. Relative to the floor, you are still. Relative to the sun, you are moving at about 30 kilometers per second. Relative to the galactic center, more than 200 kilometers per second. Relative to the cosmic microwave background, somewhere around 600 kilometers per second. All of these are correct. None of them is the real speed. The real speed is the one that does not change. The one that cannot change. The one that is the same for everything in the universe. The space-time speed. The speed of light. We are moving at exactly the speed of light. We have never moved at any other speed. And we never will. This is what the universe is. This is what we are inside it. There is a sense in which the atoms in your body are the most travelled objects you will ever know. Every atom that makes up your body was forged inside a star. The carbon, the oxygen, the nitrogen, the iron and calcium and phosphorus, none of these elements existed in the early universe. The Big Bang produced primarily hydrogen and helium, with trace amounts of lithium. Everything heavier was produced later, inside the cores of stars, through nuclear fusion reactions that took place over millions or billions of years. When those stars reached the end of their lives, they expelled their contents into the galaxy. Some exploded in supernovae, scattering the heavier elements they had produced across enormous volumes of space. Others shed their outer layers slowly, enriching the interstellar medium with the products of billions of years of fusion. The atoms now in your body drifted through interstellar space as part of that expelled material. They moved with the galaxy, orbiting the galactic center, caught up in the same large-scale motions we have been discussing. Over millions of years, some of those atoms found themselves in a collapsing cloud of gas and dust that would eventually become our solar system. That collapse happened about 4.6 billion years ago. The cloud flattened into a disk. Most of the material fell to the center and became the sun. Some of the remaining material clumped together under its own gravity and formed the planets. The atoms that were to become you were part of the material that formed Earth, and they have been on this planet for 4.6 billion years. But during those 4.6 billion years, the entire solar system has been orbiting the galactic center. It has completed somewhere between 18 and 20 full orbits since the solar system formed. The atoms in your body have travelled an enormous distance through the galaxy, always at roughly 220 kilometers per second relative to the galactic center, always being carried along with the sun's orbit. And the galaxy itself has been moving through the cosmos during all of this. The atoms in your body have participated in every layer of cosmic motion we have discussed. They have travelled through the galaxy for billions of years, moved through space at hundreds of kilometers per second, and through space-time at the speed of light, all before ending up, for now, in the configuration that constitutes you. The question of how fast we are really moving is also, in a deep sense, a question about the history of matter. about the path those atoms have taken from the cores of ancient stars, through the interstellar medium, through the forming solar system, through billions of years of Earth's history, to this moment. The atoms have been here for an enormously long time, and they have been moving through space-time for all of it at c, the only speed anything ever moves through space-time. The question of what speed even means in the context of the expanding universe is worth examining one more time. When astronomers say distant galaxies are receding at fractions of the speed of light, or even faster than light in some cases, they are not describing motion through space in the ordinary sense. They are describing the rate at which space itself is expanding between us and those galaxies. This distinction matters because it means that the recession velocity of a distant galaxy is not a fall velocity in the spacetime sense. It is not a motion of the galaxy through spacetime. It is a change in the distance between two objects caused by the growth of the space between them. The expansion of space does not violate the rule that nothing moves through space faster than c. Galaxies beyond the Hubble radius, the distance at which recession velocity equals the speed of light, are indeed receding faster than c. But they are not moving through space faster than c. The space between us and them is simply growing faster than light can cross it. This is a real and permanent distinction. The speed of light as a limit applies to motion through space, which is governed by special relativity. The expansion of space itself is governed by general relativity and has no comparable speed limit. Space can expand as fast as the physics of dark energy and the universe's total energy content allow. What this means for our own cosmic motion is that there are effectively two kinds of motion layered on top of each other. Our peculiar velocity, the motion of our galaxy through space driven by gravity and the structure of the cosmic web, is subject to the fall velocity limit and the rule that all space-time motion totals c. The expansion of space is something else entirely, a growth in the metric of the universe that carries objects apart regardless of their peculiar velocities. We live in both regimes simultaneously. Our local motion through space is constrained by relativity. The large-scale separation between us and distant galaxies is governed by the expansion. Understanding the full answer to how fast we are really moving requires keeping both regimes in mind and recognizing that the word moving means something slightly different in each. The night sky is a record of motion. Every star you see is in motion. The stars appear fixed only because their distances are so enormous that the motion produces changes in their apparent positions too small to detect over a human lifetime. Over thousands of years, the stars shift enough that the patterns we call constellations change shape. The light from each star left its source years, decades, centuries, or millennia ago. What you see when you look at a star is not where the star is now. It is where the star was when the light you are seeing was emitted. The star has moved since then. In some cases considerably. The Milky Way band across the sky is a cross-section of our own galaxy, seen from the inside. The stars in that band are at various distances, some a few hundred light-years, others tens of thousands. They are all orbiting the galactic centre, each on its own slightly different path, all at roughly similar speeds, so the band holds its shape from our perspective, even though every star in it is in motion. The individual stars within that band are not stationary even relative to each other. They have their own peculiar velocities, their own small deviations from the average orbital motion of the galaxy. Some are moving slightly faster than the galactic average, others slightly slower, each following a path through the galaxy that will take it gradually in a different direction from its neighbours. Over millions of years, the groupings we see now will drift apart, the stars separating into different parts of the galaxy, while new groupings form as other stars drift together. The night sky is not a fixed picture. It is a momentary snapshot of a continuously evolving arrangement, frozen to human eyes only by the brevity of our lives compared to the timescales on which it changes. The light from the faintest galaxies visible with telescopes left its source billions of years ago, when the universe was young and the galaxies were in different configurations than they are today. Those galaxies have moved since that light was emitted. Some have merged with others. Some have been disrupted by gravitational interactions. The universe we see when we look at very distant objects is a snapshot of the universe as it was, not as it is. We are embedded in this moving, evolving, flowing structure. We are not observers standing outside it and looking in. We are participants. The same laws that govern the motions of distant galaxies govern the motions of the atoms in our bodies. The same space-time geometry that describes the curvature of space around a massive star describes the curvature around the planet beneath our feet. Motion is not something that happens to the universe. It is what the universe is. A four-dimensional structure in which everything participates, in which every object follows its geodesic, in which everything moves through space-time at sea, and in which the question of how fast you are really moving has only one answer that is truly universal. Step outside tonight if you can. Or close your eyes and sit with the room around you. Feel the stillness, not as illusion, but as the thing it genuinely is. You are at rest relative to the world around you. That rest is real. That is a valid measurement, and at the same time, you are being carried by the planet, by the star at the center of this system, by the galaxy, by the slow drift of gravity that has been pulling the matter of this part of the universe toward its neighbors for billions of years, by the expansion of space itself, stretching the distance between this galaxy and the ones beyond reach. And beneath all of that, beneath every layer of spatial motion that astronomers have measured and mapped and argued about, you are moving through time. Right now. This moment. At the speed of light. Every second of your life has been a light second of travel through the time dimension. You have been moving faster than any spaceship ever built. Faster than the fastest particle in any accelerator. You have been moving at sea, the way everything moves at sea, by simply existing in space-time and letting the universe carry you forward in time. The question of how fast we are really moving has no single spatial answer, but it has one complete answer. We are moving at the speed of light. We always have been. Good night.